Yes, so can you listen me and
Yes, sir.
Yes, sir.
can you
Yes,
see
sir.
the slide now? Which slide is visible to you?
Footing definition.
Footing.
Okay, so next part of this lecture is the foundation definition. What are the footing and what are the different types of footing? Under which condition, which footing is suitable? You are providing that. Here in these slides, we will discuss in detail. You know that the footing is a structural member that is used to support the load and to transmit the load to the soil underneath. So in such a way that the load bearing capacity of the soil is not exceeded. So bearing capacity that is developed under the foundation bearing pressure should not be larger than the bearing capacity. That is important. What happens if your check is not satisfied? The soil can fail. Soil can fail in shear or soil can fail in settlement. So based on that, you first of all, it is important that which type of the footing you select, and then next question is finding out the pressure. For example, if there is a wall, you can go for the wall footing. Either it is a non-structural wall like a masonry wall, as you can see on the RCC pad. So wall footing are used to support the structural wall that carry loads for the other floors also. And even for the non-structural part, I can give an RCC, simply RCC pad, which is larger than the width of the wall. When your building column spaces is larger and the load is also lesser acting on the columns, as you can select the isolated footing. So isolated footing is a good option, but normally for the lesser load, for lesser number of stories, when the soil is also good and there is lesser chances of the differential settlement. Because you know that due to the larger load, the column having a larger pinching shear area, so you can see in the bottom zone, the thickness of the pad is larger in the column vicinity to avoid the pinching shear, and it is lesser at the end because there is a zero shear at the end. So isolated footing is a good option, but if the area of the footing is too wide, like you compute and the area comes out to be like 200 square feet or like that, so then you are not going to go do that. But if you see that the size of the footing is in good range, 8 by 8, 9 by 9 feet, it's fine. But if the size of the footing is too large, it comes out to be 15 feet or 6 meters, so then I am not going to select the raft footing. Then better to join the footing. You can join the two footing, and that is called as the combined footing. Combined footing usually support the two columns or three columns not in a row, because combined footing are used when two columns are so close that single footing cannot be used. So when one column is located or near the property and one column is at the edge of the footing and other column is in the interior zone of the building, you can join these two footings. So when this is a combined footing is basically the joining the two footings. When the area is overlapping and when the columns are too close, you can join the two footings. So that is called as the combined footing. Sometimes the areas are not overlapping. Still, one column is exactly at the edge of the building, at the edge of the footing, and one column is interior column, like you can see here in this diagram. So then the area is not an issue. Area is not an issue, but the force transferring is an issue. You know that the edge column will develop a movement. A movement is also there at the edge column and interior column. So how to balance that movement? How to shift the forces of that movement? Because the footing is also eccentric, is also edge. So you can understand that if I put a load exactly at the edge of the plate, what happens? It can bend, it can overturn. So to transfer the forces and to reduce the overturning of the edge footing, we can join, and to transfer the unbalanced movement at the edge footing to the interior footing, I can join it by the beam. So this beam is not taking any soil pressure. This is only transferring the movement, unbalancing momenting from the edge footing to the interior column. So this beam is called as a strap footing. Remember, this is a difference. Strip is different, strap is different. So strip footing was the first case that I have shown you. Under the wall footing is called as a strip footing, but this is a strap. Strap is a beam which join the two columns, and exterior footing and the interior footing, and this is basically used to join the two foundations. And you see that this is not the taking the soil pressure, because when we are making the strap beam, we are making it slightly above the footing base. Why? Because if I make it exactly in the line up with the footing base, it will start taking the soil pressure. So I don't want that the beam should take the soil pressure, because I am not designing the strap for the soil pressure. That's the reason. So this is a strap. When you see that more this building is a taller building, more number of stories, all the footings are overlapping and columns are also at normal spacing. Kind of very good footing, we can join a multi-column. This is called as a multi-column footing, the continuous footing. When this footing basically is supporting a row of more column, 3 column, 4 column, 5, 6 column, they have limited width. The advantage of this footing is that the width will be less because the length is quite more. The length of the footing may be in the length of the building equal to the length of the width of the building, but the width of the footing will be lesser because the area is mostly covered by giving the more length. More is the length, lesser will be the width. And of course, this footing is good in case of continuous footing, or I can join this footing. There is another type of the footing which is linked with this footing, a footing beam. I can join all the columns by footing beam also, and practically I am giving that type of footing also, because that is also another good footing. Because in this punching is there, but if I provide that a beam from column to column, then the punching is also eliminated. And that in case of seismic zone also, this continuous footing also play a good role, because this become a grillage footing. If I provide the beams in two foundation, the column at the base and hold all the columns together. So overall, it makes a building as a one unit and resist a lateral load also, and not only resist the lateral load, but also the transfer the vertical load evenly to the soil, and also avoid the uneven settlement or the due to the soil varying soil conditions. So this is a good footing, continuous footing, when we join the footing of the column in one line or in two line. But sometimes the continuous footing become, if you see that you are giving a lot of continuous footing and this is making confusing, and the cost of the footing is also going high. So then you can think to reduce the cost and rather than making a lot of continuous footing and footing beams, you say that, okay, no problem, the areas are very close, the areas are overlapping, soil is also not good. So then you say that, okay, we can provide a single plate under all multiple columns. So that single plate footing, single thick plate footing under a more number of columns is called as the raft or the mat foundation. So this footing is very common for the multi-story building, because the load is quite heavy and all the load is to be transferred to the soil. The soil is maybe weaker, because when the area of the footing for the isolated is very larger, and even for the continuous beam, you see that the width of the footing is coming out to be very large. You can say that, okay, no problem, you can just join all the footing, because making a raft is easy. You can make a raft in one go. So rather than making a lot of 100 separate footing, you can say that, okay, no problem, you can make a one single footing. And this is a common footing for the tall building, multi-story, because one is the capacity of the to take the load, and settlement also, it can handle a larger settlement, and it make again the one unit, the whole building is transformed to the one unit, and it make a very stiff foundations. So this basically soil act as a spring, and all the load is properly transferred to the spring soil underneath by this kind of foundation. So this is indeed a good footing. So that is called as the mat or raft footing. But always isolated good, combined option. If that is not good, we go for the multi-column option or the footing beam option, grillage option, and then last is the mat option. So that was about the isolated footing. Now comes out to the deep foundations. You know that the deep footing is provided when in the reasonable depth, up to the reasonable depth, you don't find any good soil. and you say that the bearing capacity is very low, soil is not good, and then you have to select the deep option. Or if the load is excessive, for example, the bridges, overheads, flyover, you can see in the orange line also there is a larger heavy column pier, and pier is then transferring the load to the pile cap, like you can see in this figure, and pile cap is transferring the load to the piles. Piles are under the pile cap, and above the pile cap is the pier. This is a very good option, and piles are basically provided. Piles are not necessary for the bridges, because even in the buildings the pile option is provided. You see the packages mall in Lahore. We have read that design by the civil department, and we have seen that they were providing the pile foundation because they thought that the piles are cheaper than the large mat or raft footing. So they go for the pile option in that building. So this is possible that the piles can be under the buildings, also under the bridges, in the river zone, in where the largest cover depth is expected. So under the bridges, so this pile foundation is basically a deep foundations that you are designing for the many kind of structures. Pile load test is carried out, and then the piles are provided. So that topic was about the distribution types of the footing, and now we are discussing the soil pressure distribution. You know that the soil column load is acting on the centroid of the footing, and when the column load is acting at the centroid of the footing, the pressure under the soil, under the footing will be a uniform pressure, and that will be that can be computed by the load over area. And however, the actual distribution of the soil is not uniform. You know that sometimes due to the cohesionless sandy soil, the pressure distribution is shown on the left-hand side figure, and due to the clay soil, the pressure distribution is shown on the right-hand side figure. So it's very interesting that, but we assume it as a uniform. Actually, for the clay soil is at the right-hand side, it is taking more load at the edges, lesser in the center. So, and I have shown you the pressure in detail actually today in the first part of the lecture. So here the design consideration, footing must be designed to carry out the column load and transmit them to the soil safely. And the important parameter in that is the area of the footing based on the allowable bearing soil capacity. The area of the footing should be properly determined by the allowable soil capacity. Two-way shear, because the depth of the soil, depth of the footing is controlled by the punching shear. So you must satisfy the punching shear check especially, and one-way shear. And bending is also bearing pressure should also be satisfied. The fourth one is the bending moment and the steel required. The bending moment should be computed, and the steel required. You must know that the where the tension is developed, and then you can decide that what kind of the movement is present. I will add some of that slide regarding the bending moment of this isolated footing and combined footing, so it will be clear. But not only the foundation steel is important, but bearing capacity of the column, that you are resting the column on the footing pad. So you have to see that whether the column is capable to transfer its load to the footing. Sometimes the failure occurs because the column was very heavy and the footing pad was lesser thick. So you have to see that the column can transfer its load to the footing. Dowels, you have to transfer the column movement to the footing actually. So dowels are provided. These are the L-shaped steel, which is also embedded in the column and also extended in the footing. The steel which is lapped with the column steel and extended to the foundation steel is called as the dowel steel. So dowels are designed. How much dowels are needed? 4 dowel, 8 dowels. So you have to compute the dowel requirement, and dowel development length topic you will study in the other lecture. And from that you can compute the development length, that how much is needed to lap length, splice length, and extension length of this dowel reinforcement in the footing. Then you must satisfy that the differential settlement is avoided and how much distortion is for the building. You can compute this in the soil geotechnical part you have studied, and after you design the footing you can apply the settlement equation and see that what possible settlement will occur for this foundation, and that should not exceed the allowable settlement, 1 inch or 3 inch, whatever, depending upon the type of the footing. So for the size of the footing, you will consider the service load, but for the strength of the footing design, structural design, you will consider the ultimate load. So area of the footing is the total load divided by the allowable soil pressure. The area of the footing can be determined from the actual external load such that the allowable soil pressure is not exceeded. And when you will go for the structural design, you will make the factored load. So factored load divided by the provided area of the footing will be computed. And you will design the footing steel for the factor loading. You will compute the area for the service loading. This is the differential settlement that how can one building can settle with respect to the height and length limit. So if your length of the building is width of the building is L and height of the building is H. If it is less than 3, then your maximum distortion allowed is 1 in 3300, and in sandy soil, and 1 over 2500 distortion is allowed in the clay soil. But if it is L over H is larger than 5 for taller building, the distortion allowed is lesser. It is 1 over 2000 for larger than 5 L over H value, and so on for larger 1 over 1400 for larger than 5 L over H value in clay. So this one is basically the distortion, and so this was about the basics of that. Now what are the steps involved for the foundation design? First you get the load from the analysis, you get the allowable bearing capacity from the soil report, you compute the net allowable bearing capacity by subtracting the overburden from the allowable capacity, and you then compute the area of the footing required. That is the load over the net allowable bearing pressure, because net allowable is to be determined, and you get the area of the footing, and from that area of the footing you determine the safe pressure Qn, the service load pressure, and the ultimate load pressure Qu. Against the ultimate load pressure you determine the shear, applied shear and applied moment, and you check the satisfy the one-way shear 5EC check and the punching shear check. If those are satisfied, you go ahead for the moment computation and steel reinforcement computation, and if the check is not satisfied, you revise the depth and then redesign the steel reinforcement. You compute the steel in the shorter and the longer direction of the footing, and then you go for the double bar design, that is called as the joint design, and the splice length and the development length of the reinforcement. And if all these designs are done, then you go for the preparation of the foundation plan and section drawings. So starting with the different aspects, that how to get the shear and the moment in the footing. So footing may fail in shear as a wide beam or due to the punching. These are referred as one-way shear and two-way shear respectively. So this concept of the one-way shear, two-way shear is very much similar as we have discussed and seen in the flat plate system. You know that the one-way shear is critical at a distance d from the face of the column, and two-way shear is critical at the distance d by 2 from the face of the column. Two-way shear is a punching shear. If the steel reinforcement, if the shear is not satisfied for the foundation, you no need to revise the, no need to provide the shear reinforcement, but you should revise the thickness of the footing. What is the one-way shear computation value? So again here in this slide, one-way shear is only calculated in the longer direction because it will be smaller along the width. It will be more along the length. So applied one-way shear is given as a Q and U into B, the net the pressure factor load into the width B, because normally we compute the one-way shear across the full width of the footing. So into B, full width is multiplied, and the distance, that is a shaded part. I have told you that one-way shear is critical at a distance D from the face of the column. So you can compute the one-way shear from L minus C1, column size divided by 2 minus D. So this will give you the critical one-way shear at a distance D from the face of the column. One-way shear check must be satisfied by 5 EC, 5 over 6 under root FC prime BD, because you have considered the full width. So also in the 5 EC check, you will consider the full width. So one-way shear check is should be satisfied. And if the one-way shear check is satisfied, not satisfied, then you can compute the revised depth by this expression. D is equal to VU divided by 5 over 6 FC prime B. If the one-way check is not satisfied, you can compute the depth. You can revise the depth and compute the revised depth from this formula. You can also equate the equation of the punching shear and the applied punching shear by making the D as unknown, and you can also compute the value of D there. But normally, practically, to save the time, we assume some depth initially and we check that whether the check is satisfied or not. So this is important, that the depth should be satisfying the one-way, two-way shear criteria. The ratio is also important, that the which is the punching shear and applied shear ratio should not be too large that it is an uneconomical design, and it should not be less than 1 that it is failing in punching. So if it is 1.2, it is fine, but if it is 5, it is uneconomical, and if it is 0.8, it is, you have to revise the depth. Because the punching shear is more critical, so that decides the depth of the footing. So many tests have been carried out in the lab experiments where the punching shear different options are studied, and you can see the failure of the column is happening due to the punching shear, where soil is taken as the spring and the load is applied. So two-way or punching shear method is very similar as in the flat plate system. You compute the perimeter, punching shear perimeter, that is C1 plus D plus C2 plus D, 2 times of that. And the punching area is basically the area, what is the critical punching shear force? That is the load acting at the base of the soil, pressure, multiplied by the area outside the critical punching perimeter. So you just take the area, total area of the footing, and subtract the area within the punching perimeter. So L over B is the total area, and the area within the punching perimeter is B1 and B2, where B1 is C1 plus D and B2 is C2 plus D. So you can subtract, that is a very much similar to total footing minus the area within the punching perimeter. You can find out the punching shear. And your punching shear, there are 3 checks which are the similar check that we applied for the flat plate system. So there are 3 checks provided by the ACI code, and you can compute the value of the punching shear, beta C. All these values are known, alpha S. Put down the values, and minimum out of the 3 criteria will be selected as the punching shear strength. And punching shear strength should be larger than the applied shear. Next on the moment computation. So moment, first you must know that what is the critical section for moment. If the RCC column is made, the critical section will be at the face of the column, and if the masonry wall is made above the footing, the critical section will be the middle of the edge of the wall and the face of the wall. And if the steel base plate is given, then the critical section will be at the face of the base plate and the middle of that. So edge of the base plate and the middle of that. So S by 4 in that case. So you can see that the critical sections are shown by the red line here. For first case is a RCC footing, second case is a wall footing, third case is a steel plate footing. So the critical section is shown by the red color line. Now the moment computations, I mean, you can compute the moment for the full width, or you can compute the moment for the 1 meter width. So that is not difficult. You just take the UDL, and the critical section is at the face of the column. So moment computation for the concrete footing will be QU, the load, into 1 meter width, or if you are taking for the full, then you can multiply it with the B also. If you take it as a 1 meter, you are getting the steel in 1 meter area, and if you are taking it as a full width, you are getting the steel for the full width. So for symmetrical UDL loading, I can take it as a 1 meter, but if it is an unsymmetrical loading, a trapezoidal loading, you can take it as a full width. So QU into 1 over 8, L minus C1 by 2 is the moment length, and L minus C1 by 4 is the movement arm length. So it is simple, just UDL is acting at a length of L minus C1 by 2. So you just multiply the UDL value with the moment arm, which is L minus C1, where L is the length of the footing, C1 is the column size, and you can determine the moment as QU into L minus C1 square over 8. And the movement across the width of the footing will be different because the dimensions of these footings are different. So if the dimensions are different, you will compute the separate movement across the width. So across the width of the footing, for 1 meter wide strip, the movement will be QU into B minus C2 by 2 into B minus C2 by 4. So this will be the movement across the width of the footing. So the isolated footing, the movement is not difficult, and you can compute the moment in the isolated footing. These are the minimum steel requirement for the grade 60 and grade 40 steel. For the grade 60, the minimum steel is 0.0018, and for the grade 40, the steel requirement is 0.002 BH. And then come the design of the joint design, the transfer steel. So we will continue with the this part next time, and then we can start the problem of the footing after that.
Okay, sir.
If you have any question, that's all about the footing lecture today. It was a lot of topics are, and try to initiate some computation of the footing area yourself and bearing capacity. Try to study the soil report and work on these aspects of the footing design. Now, if you have any questions, you can ask.
Excuse me, sir.
Yes.
सर ये टॉपिक किस रेफरेंस बुक से है?
Books are basically, you can't say any fixed book again, because it's like maybe from the Nielsen, like it's not from any book actually. Some of the topic is from the Nielsen. Actually, all the books are giving the details of the design. You can follow any book. Reference all the books. I have told in the first lecture that all the books are the reference books, and all the thing that I discussed in the class become the part of the course. So course, I will design some footing from the book by Nielsen, some by the book by Zaid Siddiqui, and some from some other book. It's not fixed like. I will be giving you, I have given you one complex engineering project in which the footing have to be designed. So in the books, they are just giving the one example problem of isolated, one combined, and they are not discussing in detail that how to get the load on the footing. So normally I have initiated from the first principle, that starting with the first step and then going further. So actually you must, I will provide you the handouts of the footing and the ACI committee report for designing the continuous footing. I will also, I say that you must read those ACI guidelines, and the books, all the books are which are explaining the foundation design by ACI requirements are good books. So these can be a McGregor book by Nadeem Hussain, Zaid Siddiqui Saab book, and Nielsen book. Any book can be found.
Okay, sir. Kindly handout sir जल्दी share कर दीजिएगा, मतलब जिसमें details ज़रा.
On this weekend, I will share these video lectures, and if can you access my lectures after the. Please let me know that because these lectures are available on MS Teams, and if you have the official account UET ID, you can listen the lecture live. But if you don't listen, then I have to download the video lecture and then share it like some other ways.
सर अपलोड कर दिया करें, डॉक्टर काजी भी ऐसे ही करते हैं, वो ना कुछ लोगों को एक्सेस नहीं होती उसकी.
Okay, then on tomorrow or on Saturday, I will download this lecture because this is a 2-hour lecture. So I will download and then we'll share with you.
Okay.
And notes I will share with you today. this notes and the DDM problem. I will share. Meanwhile, you can ask the question by sending the messages, separate messages to me, just to me, and ask the question rather than putting on the journal wall. You can, I think, send me the message, or you can write down all the questions. The CR can write and send me that through the WhatsApp, and I can answer together all the questions related to the lecture. Try to work on it and get practice for this and read the relevant literature, especially for the pressure distribution diagram. Practice the different cases yourself for the uniaxial case or biaxial cases foundation design, and it will be interesting. And for the complex engineering project also, you have to design the foundation. So you must know from the first step, then you can proceed properly.